And we're back again with temperature. So temperature is the measure of the average kinetic energy for your individual particles in motion. Okay, and this we will contrast with heat in a second. So what the thermometer does is just say how many times does a particle hit itself or hit the thermometer. If you get more particle impacts, then we increase the level of liquid inside our thermometer. Less particle impacts means less particle impacts per individual time frame means a lower reading on the thermometer. Okay, so all it's doing is measuring our average energy within that system. How many times within an individual time frame, on average, is it getting impacted? There are 3 different scales that allow us to monitor this. Why would we have so many different scales? Well, we're able to note that there are different temperatures. We can feel that average energy every time we walk into a different room. Right? We can feel a change in the temperature, a change in that, and we get goosebumps or we start sweating. So because it's such an obvious observation, tons of people have attached ways or numerical values to it, which then means we need a unit system for it. So there are 3 commonly used temperature scales. We get the Fahrenheit temperature scale, which I'm calling as English. Then we get Celsius, which is the most commonly used. And then we get Kelvin. Kelvin tends to be the one used in calculations, which we'll see later in this unit as well. Okay, Kelvin is an absolute temperature scale, so there's a lot of physics and mathematics that build behind it. Fahrenheit and Celsius are all relative scales. Okay, they're relative ultimately to water or whatever was available for us. So if we look at some common values for Fahrenheit, water numbers, it freezes at 32 Fahrenheit and it boils at 212. Okay, and you might wonder why they picked those numbers. The more interesting one to me is that 32. Okay, why pick a freezing point for water, the most common thing, to be 32? Well, when Fahrenheit created it, he was able to recognize that there were things colder than ice. Okay, we could get colder than ice. If we can get colder than ice, then ice shouldn't be a 0, because if it is a 0, then we get negative values. And as we've discovered when we looked at redox and all sorts of other chapters, negative values are not fun to deal with. So he picked a 0 point to be the lowest cold temperature he could find. Okay, it turned out to not be the lowest, but that's what he picked. Okay, and then he adjusted his scale thereafter. If we look to Celsius, Celsius is picked at water as 0. Okay, yes, we could go colder, but if we went colder, we just incorporated minus signs and we just said we didn't worry about it because we didn't know exactly where it was. Water was the most important thing anyway, so let's center everything off of water. Okay, why go up to 100? Because we're looking at factors of 100. We're basing this sort of off of the SI system, okay, or our metric system, where we're doing powers of 10. So that made the most sense for our graduations. When we go into Kelvin, the common water numbers become a little bit bizarre. For our freezing point for water, it's 273 Kelvin, and for the boiling point, it's 373. A quick note, you'll notice that there are degrees written next to our Fahrenheit and our Celsius. There should not be degrees written next to our Kelvin, because Kelvin's an absolute scale. There aren't degrees, and degrees are effectively arbitrary markings. Okay, so the Kelvin is a lot more restrictive and precise in those values than our Celsius and our Fahrenheit. And you might wonder about why we picked those numbers for Kelvin, and that's because Kelvin is based similarly to Fahrenheit. It's making sure that we don't have a negative value. Okay, so based off of physics and mathematics and chemistry and all sorts of hardcore sciences, we can establish that there is a lowest temperature value. Okay, and that lowest temperature really has to do with our energy. It's when we have 0 energy. Well, if we have 0 energy, we have a 0 temperature. So we can abstract backwards in plots to figure out where that 0 is. Once we've got that 0, now we've got our markings for everything else. okay, up to 273 or beyond 273, but that's where those numbers are coming from. Since we have different unit systems, of course we need different conversions between these. I will provide you the Celsius to Fahrenheit on tests, largely because I don't have it memorized, so I'll give that one to you. The Fahrenheit to Celsius one, I expect you to derive. So if you're given the Celsius to Fahrenheit, you should be able to do the algebra to go Fahrenheit to Celsius. Okay? So I won't give you that middle one. You have to figure it out. And then the last one, to get to Kelvin, we have to convert from degrees Celsius. So degrees Celsius plus 273 gets us our Kelvin. Okay? You'll note there's a 0.15. It's not worth worrying about. 273 is all you really need to know. So add 273 degrees Celsius and you've got your Kelvin. This is one that you need to memorize because it's an important conversion factor and it's a relatively straightforward one. Okay? Which then gets us to how we could potentially solve questions. So we'll delete the one that I expect you to derive. If I want you to solve for the body temperature, 98.6 degrees Fahrenheit, a pseudo-directly relevant question for our current system, what is the body temperature in degrees Celsius and in Kelvin? Okay, so feel free to go through and tackle this. Okay, now that you've had an attempt, because you paused the video and went through and did your own solves, we can go through and look at it. There's a couple ways you can do this. We could go through and say Celsius 9/5 plus 32, 32 equals 98.6 and start plugging and chugging with our math. Okay, minus 32, and all that fun stuff. Okay, and yada, 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 and get a degree Celsius. My recommendation is to not directly sub in, but to do the algebra first. So Celsius is 9/5. This equals Fahrenheit minus 32. Celsius would be Fahrenheit minus 32 times 5/9. And now I would do the sub in of my values. 98.6 minus 32, 5/9. This minimizes the amount of calculator steps that you have to go through and initiate, which is why I would recommend that path to getting through to your Celsius. If we go through and do that, hopefully what we end up getting for an answer when you enter it all in is something darn close to 37, if not 37 exactly. No, it is 37 exactly. So our degrees Celsius would be 37 degrees Celsius. All right, to get Kelvin, we have to add 273 to that. And if we add our 273, we get 310 Kelvin. So really there are two answers. Okay. When it comes to sig figs on this, I will fully admit I am all sorts of sketchy and weird on this. I'm not going to test you on sig figs when it comes to temperature conversions. Heat. So while temperature measured our average kinetic energy, heat is the measure of total energy. Okay? Because it is a slightly different measurement, we get a different unit system. The unit system that we get for heat is typically in joules or calories. Okay? Depending again on who won out in that particular discussion. Heat is different from temperature. Okay, how so? Well, if we take a look at these two containers, okay, they're both at 100 degrees Celsius, and yet one of them has more heat than the other. Which one is that? Well, this one has a larger heat than the other one. Why so? Well, there's more in it. There's more substances, which means each of those substances has potentially the same temperature, average energy as beaker A, but there's now more particles there, which means if we say spilled this on ourselves, the larger volume at that temperature is going to hurt a hell of a lot more than the smaller volume. Okay, this is why you can't sue McDonald's for spilling a drop of coffee on yourself, but if you spill the whole cup, now it becomes problematic. Okay, so be aware of that when we're looking at heat. So total energy. The next thing that can come with this is that each substance will respond to heat differently. So we get a physical property, an intrinsic property of a substance, and we know that as the specific heat. Okay? It is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. And what this gets us to is a conversion factor that allows us to relate calories to joules. This particular numerical system here is what's picked out for water. Okay? Why water? Water is the most common substance that we'd be dealing with specific heats in. Okay? The larger the specific heat, the more heat is required to raise the temperature. Okay? So if we think about some examples real quickly, let's pick something of 4,000 joules per gram degree Celsius versus something that is, let's just do 1 joule per gram degree Celsius. What this is saying is I have to put in 4,000 units of heat, okay, or units of energy to make 1 gram go up by 1 degree Celsius. Okay? Since we're comparing these two systems, the bottom of these is the same. Okay? The top is really what's different. I have to put in 1 unit of energy versus 4,000 units of energy. Okay? So the 4,000 units of energy means I have to put in a lot of energy to cause the temperature to change, which means that substance, whatever it is, does not allow for the passage of heat well. Okay? That would mean it would be, might be useful to color code, an insulator. Insulator. Okay? It doesn't allow for the passage of heat. If we look for the other one, well, the other one with 1 unit of energy, the temperature goes up by that same 1 degree. That's allowing for the passage of heat very, very quickly. That would be a conductor of heat. Okay? Why is this useful for us? Well, have we talked about insulators versus conductors before? Okay? Yeah, we did. We talked about it within the context of metals and nonmetals. Nonmetals tended to be insulators, and metals tended to be conductors. So if we go through and look, and this is vastly oversimplified, but it gives us a ballpark estimate at first. If we go through and look at metals versus nonmetals, our metals tend to have much lower specific heats than our nonmetals. Okay? Which gets us to a potential exam question. Which of the following substances is expected to have the largest specific heat? Okay? So if we walk through this again, largest specific heat. Lots of energy, very little change. Temperature change. Okay? If that's the case, then what are we looking at? Are we looking at an insulator or a conductor? Lots of energy, no temperature change. That should be an insulator. Insulators. Okay? What substances are best at insulating? Well, nonmetals. So what does that mean I now need to do? I now need to find which of these substances is a nonmetal. Okay? Well, how do I identify nonmetals? Okay? Hopefully you can acknowledge that our nonmetals are to the left of the staircase on the periodic table. And it would be helpful if I actually knew my left and right correctly. They're to the right of the staircase on the periodic table. Okay, so we could look at the periodic table to determine our answer. But the periodic table does not give us the names of compounds. It gives us the symbols. Okay, which means we have to have spent some time to memorize the names, to be able to convert to symbols, to be able to evaluate where they are on the periodic table. So this question is on the surface just asking which is a nonmetal. Okay? But at that same time, it's also asking a question about nomenclature, because not all of the answer choices are written with symbols, they're written with names. Okay? Again, this is getting you thinking about what you have to think through to get an answer right on an exam. There's lots of different steps that you have to move through. Okay? Because I know you probably want the answer. In this case, our answer is going to be carbon because it's the only one that's a non-metal on this list. Okay? How could we change this? Well, we could say which of the following is expected to have the smallest specific heat. Okay? That makes things a lot more difficult in this case because all of these are metals, and we haven't specified that, okay, on how to nuance within a class. So what would have to change about the question? Well, the rest of these, or some of them, would have to become non-metals if we switch this to smallest. Hopefully that makes sense, as I'm not very creative in coming up with some non-metals. Okay, and then with that, we still got a little bit of temperature and energy here, so we'll keep going. We do have the law of conservation of mass and energy, which is something you've probably already read about or heard about. Einstein came through and gave us the fancy equation E equals mc squared that allows us to see that there's a direct relationship there. We've used the law of conservation of mass and energy when we balanced chemical equations because we couldn't destroy matter through the process of those equations. Okay? You won't be expected to do any calculations with these, at least within my class. But if you have to take more or future chemistry classes, they will probably have you run calculations with these. Conservation of energy. Einstein went through and established this, but this becomes important when we consider all of the different phenomena that we deal with as chemists. Okay? There are 6 primary forms of energy. Okay? Arguably, we're looking at 2 or 3 of them in the picture there. Okay? Those 6 forms of energy: heat, light, chemical, electrical, mechanical, and nuclear. For those of you that are physicists, stop telling me about the 3 different forms. This is the forms of energy that we're looking at. Okay? So, what's happening here? If we look at that picture, we are applying heat to this. Okay? That heat causes a phase transition. Okay? We're now causing the liquid to move more when it transitions to a gas. So more motion means we're now introducing kind of a mechanical. We've got motion coming out of that. Okay, well, where did the heat come from? The heat came from burning gas. Okay, burning gas was a chemical reaction. That chemical reaction produced heat, which then was translated into a mechanical energy. Okay, this works to heat up our food so that we can then drive water into our food to hydrate it and potentially cook and kill pathogens, and that's how we get our food. But are there other ways that we could convert energy? Well, if you consider the system that we're watching right now, you are visually seeing light. Well, where is that light coming from your screen? Well, it's coming from an electrical energy. That electrical energy is coming out of the wall. Okay, and that wall electrical energy is now coming from somewhere else. Okay, usually it's coming from mechanical energy. That mechanical energy could quite likely be the boiling of water, which means our mechanical came from our heat energy. Okay, heat causing water to boil, which caused a turbine to move, and there's our mechanical. Well, what caused the water to boil? That water boiling was our chemical energy coming from petroleum. Burning of petroleum to generate hot water so that the gas moved past a turbine to cause the turbine to move to generate electrical energy. The electrical energy was transported to your house so that you have light energy. Okay, well, one of the things that's kind of problematic within all of these conversions is that heat is a loss in every single step. Okay, so heat happens in all transitions. Okay, so we always lose some energy as heat. We can't capture it all. Okay, and that means the more of these steps and arrows we've got, the less precise our system becomes. Okay, so how could we have simplified this? Well, why did you need the light? You needed the light so that you could learn. Well, instead of using light from your computer to learn, maybe we should be in a classroom where I'm now teaching you. Right? So you're in that one-on-one interaction. So now you don't need that light. We're together. But if we're in a classroom, it's dark. So we should have our classrooms outside. So all of our classrooms should be outside classrooms, so we have the sun on us so that we can actually see and communicate. Okay? But therein lies another problem, particularly in this state. It gets bloody hot during the summer. So we would need to move inside. But as soon as we move inside, it gets dark, so we need light. Where do we get the light from? We could build sunlights and skylights. Okay? We've decided to build electrical because it's more efficient for us to get light in and still be comfortable. Well, where do we get that electrical energy from? Okay? If we go to mechanical systems, okay, those can become challenging, but that's pretty much our next step is to go to mechanical. So where do we get that mechanical energy from? If we go to chemical, we get some of that loss as CO2, pollutant in the atmosphere. So we might instead switch it up and go nuclear, okay, to minimize some of that external pollution. We then have some issues with the nuclear as well. Okay, so how else could we do it? We could get it by introducing solar cells. Okay? Solar cells avoid the mechanical altogether, and they convert light directly into electrical energy. Okay? So we get kind of a nice little cyclic loop. Light produces electrical energy, which then produces the light somewhere else that we want it to be. Okay? So that's a nice little system that works out for us. But each of these stages has their own dilemmas and costs and problems, and that's why we have chemists. Okay, so let's take a little bit closer look at the mechanical energy. You'll see pictures like all three of these in varying other classes. The top one is a classic example from a physics class. Same with the lower left. The lower left might actually be more of an engineering class. Ultimately, why is the cannonball moving? Cannonball is moving because of gunpowder. What happened with the gunpowder? A chemical reaction. Physics works because chemistry. Okay? If we look at the engineering, okay, well, we're looking at the pistons within an engine. Okay? Gasoline comes in, combusts, causes the pistons to move, which then causes some mechanical energy, okay? Or mechanical energy so that we can move forward. Well, our entire engineering process is based off of chemical energy. We move to biology, which is our lower right hand. We have ATP, which is typically how it's represented in biology. We could just go ATP to ADP, and ta-da, we have energy. Well, what's happening? It's adenosine triphosphate, ATP, going to adenosine diphosphate. Because you've spent some time, and of course I underlined the wrong P in the triphosphate, spent some time looking at structures, you should be able to recognize that you have 3 phosphate groups in ATP, and when we move to ADP, we only have 2. The simple removal of that one phosphate group happens to release enough energy that we exist. Okay? That simple bond that is being broken from ATP to ADP produces enough energy to drive the vast majority of our biological reactions, allowing us to exist as humans. Okay? Kind of neat. Kinetic energy, temperature, and physical state. So we've got 3 images here: solid, liquid, and gas, which you would hopefully be able to pick out. Solid, liquid, and gas. What's happening? How do I move from a solid to a liquid? Well, I had to add energy in, okay, seen as temperature. How do I move from a liquid to a gas? Well, the same deal. Energy in the form of temperature. So as I add energy, what happened to the motion of the particles? Well, they increased. Okay. If we look at the reverse process, if I want to get those particles to stop moving, I have to remove energy. Then I have to send that energy somewhere else. Okay. So all of our phases have some form of kinetic energy. Okay. Our solids just happen to have a very, very small amount. So small that to the human eye, we don't see it, okay, or we don't observe it. But those particles are still oscillating and moving, just nowhere near as much as they are for liquids or for gases. Chemical changes, we can look at this one which I almost always skip over as a slide. If we look at water and electrical energy, we can pump electrical energy into water to make hydrogen and oxygen. And we might ask, well, why would I want to do that? Okay, well, hydrogen and oxygen can be cool because what I can do with that hydrogen is use that now as a fuel, add a spark, and that's now going to release some energy. Okay, if I build a system that can now capture that energy, like a hydrogen fuel cell for hydrogen cars, I can now convert that energy into motion. Okay, so what we're doing is creating a fuel. Okay? Hydrogen gas becomes the fuel. Why did we pick hydrogen gas? Well, the byproduct of this is water, benign and harmless for the most part, and the starting material for this is water. Okay? The big driver behind making this fuel, though, is this energy absorbed. How do I get that energy into this to make the hydrogen gas? If we think about hydrogen fuel cars, that energy in process is very commonly done with gas, okay, or oil. What's the problem with that? Gas and oil are already a fuel. By using a fuel to make a fuel, we're losing efficiency. Okay? So if we can change how we make this process, and instead of being gas, we made it solar, now we've got a way to generate a fuel that is relatively minimal impact, and we have a fuel that we can now transport and allow different things to happen with the same flexibility and storage power of our current oil system without having to rely on the cycles of the sun, which is kind of neat. And I think our last slide of this particular lecture sequence would be lowering gas bills. Okay, so if we can use our understanding of kinetic energy, how would we answer this question? Is it better to fill a gas tank in the cool morning or the warm afternoon? Okay, so if we push this to the extreme, let's say in the warm afternoon, our gas tank is now all gas phase, and so lots of space in between. In the cool morning, it's all liquid. Okay, that's extreme, that's not the case. Okay, but let's push it to that extreme. If we go to the gas station, what are we filling? How are we measuring it based off of? We're measuring it based off of gallons, the volume of gas, not the mass of the gas. And since the gas particles themselves are the ones storing the chemical energy, if I'm filling it in the warm afternoon, I'm getting less gas particles in that volume, which means I'm not going to travel as far. I'm not going to be able to have the same mileage. So it makes sense to fill up our gas in the cool morning because we'll get more particles in that tighter, compact space because they have less energy, okay, or less kinetic energy. So that's all well and grand. You can run some calculations on this if you would like. The difference in density for liquid gasoline, okay, in the cool morning or the warm afternoon is next to nothing. So next to nothing that you are probably better served to spend 5 minutes walking around the gas station looking for loose change than you are to always fill up your car in the cool morning. Okay? Just an observation or consideration. And so with that, I think that's going to shift us into, a funny joke, so we can go ahead and look at that. But that's going to move us into the next unit of dealing with a lot of conversions with chemistry terms. And so with that, we'll go ahead and stop.